All right, so remember we talked about the rate determining step. That is the slowest step. So again, when we look at multi-step mechanisms, reactions that occur in more than one step, what we want to key in on is where is the slow step. The slow step is the rate determining step. The slow step is the step that controls how fast the reaction occurs because you can only move as fast as the slowest step. So the slow step will either be first or it won't be first. So when we look at what happens, the first scenario we'll look at is what happens when your first step is slow. So what we want to look at is how do we find the rate law and what information can we glean when we know that the first step is a slow step? How can we look at the rate law and know that? Well, so from experimental data, so if you go back to what we looked at before spring break, if you look at, we're given a data table, we compare rate 1 to rate 2 or rate 4 to rate 3, whatever that might be. We could find the rate laws, rate equals K, concentration of reactants, raised to a power. Now, we look at this rate law and we would see that with respect to NO2, it's second order. But with respect to CO is not in the rate law, so we know it's zero order. Or we know that the rate of the reaction has nothing to do with the concentration of CO. So CO is necessary for this reaction to occur, but again, the rate of the reaction does not depend on its concentration. Now, looking at this, what might we look at when we look at this and know that it occurs in more than one step? Well, let's think back to what we talked about yesterday. If this was an elementary process, or if this occurred in one step, we can use the coefficients from the balanced chemical reaction as the exponents. Because the coefficients in the balanced chemical reaction do not match the exponents, we know that this occurs in more than one step. And so this also suggests, because we need CO, but CO doesn't affect the rate, this suggests it occurs in two steps. And again, we're going to look at this first step being slow. So a proposed mechanism for this reaction could be step 1 and step 2. So you start with NO2, we need two of them, they combine, they collide, they react to form NO3 and NO. Once we make the NO3, we can then have NO3 that reacts with CO, and then this is where we're seeing the CO to make the final products. And then this NO2 would then be used back in step 1 to continue making NO and CO2, which are our products. One thing to write down or key on is NO3 is an intermediate. An intermediate is a substance that is produced in one step and used up in a later step. So NO3 is a reaction intermediate. CO is not involved in the slow step. So we see the slow step. This is the rate determining step. Doesn't matter how fast step 2 occurs, we can only be as fast as step 1. Look down here. Doesn't matter how fast they get through plaza B, we have to get through plaza A first. So because CO is not in the rate determining step or is not in the slow step, you don't see CO in the rate law. Doesn't matter. We need step 1 to occur before step 2 can occur. Now, if we go back, so when we write the rate law, so when the first step is slow, if you notice, if you were to write the rate law for just step 1, you would have, this could be NO2 plus NO2, or you could rewrite this as 2 NO2. And that is where we're getting this 2 from here. These are both elementary reactions. Step 1 occurs in one step, step 2 occurs in one step. So when the first step is the slow step, the rate law of that slow first step, rate equals K, concentration of NO2 squared, is the rate law for the overall reaction. Again, I'll say it again, you should write this down. This is kind of the trick, the shortcut, what we need to remember. When your first step is slow, so if you were, and you're going to be given these mechanisms, the question will also tell you slow and fast. So I don't expect you to know, is the first step slow, is the first step fast, what is it? We're going to tell you if it's slow or if it's fast. all you have to do is say, oh, the first step is slow. So this is what I would write down. When the first step is a slow step, the rate law of the first step is the rate law of the overall reaction. One more time. When the first step is your slow step, the rate law of the first slow step is the rate law of the overall reaction. And so that's what we'll do when we have a slow step being first. Well, what if your first step is not slow? So what if your first step is fast? Now, because we're learning online and because of time, I am not going to go into mathematically how they solve it. You can click through the slides if you want. You can join the online office hours. I can walk you through it on the online office hours. But all I'm going to really do is I'm going to show you the shortcut or the trick or what we need to know to answer these questions. So this is a reaction. This is the rate law. Because this is a termolecular process, this rate law suggests a two-step mechanism. So let's talk about that. Termolecular means 3 molecules. We have 2 here and 1 here. Remember back to collision theory. If we want a chemical reaction to occur, we need molecules to collide at the right orientation and with the right amount of energy. What is the chance? What are our chances of 3 things colliding at the same time with the right orientation and the right amount of energy? That's not very likely. So if we had 4 or 5 or 6 or 10 or 15, if we had more molecules trying to collide at the same time with the right orientation and the right amount of energy, there's not a good chance that's going to happen, and so that suggests a two-step mechanism. Now, if we had 2 things that had to collide, that's more likely, so that's more likely to occur in 1 step. But because this is termolecular, it suggests it's a multi-step, and in this case, they say 2. So we could look at the proposed mechanism, right? The main thing I want to show you is they tell you the first step is fast, okay? So step 2 is our rate determining step. One thing to make note of here, step 1 is at equilibrium. The forward and the reverse reaction occurs. We'll talk more about equilibrium next week. So the rate of the overall reaction depends on the slow step. So that they wrote the rate law of the slow step, right? Rate is K, concentration of your product or your reactants raised to a power. These powers are both 1. Because if we go back here, the coefficients here are both 1. So this is the slow step. They wrote the rate law in terms of the slow step. But this doesn't help us. So when we look back to our overall reaction, we have to write the rate law in terms of NO and Br2. And when you look at the rate law of the slow step, it's in terms of NOBr2 and NO. So NO is good, but we have to have a different way to define NOBr2. And so they walk you through the different steps. They go through deriving it. Where does it come from? And so in the end, you get rate equals K, concentration of NO squared, concentration of Br2. Let's go back and let me show you the shortcut. This is all we have to know. If we look at the data, the information we're given, and we see that the first step is fast, this is what you do. Use the coefficients from your master or overall equation as the exponents. When your first step is fast, you can pretend that this occurs in 1 step. It doesn't, but you can pretend it does when you write the rate law. And when I say that, what do I mean? How should you apply that? Practically speaking, you should just take the coefficient and make it the exponent. Take the coefficient, make it the exponent. And the only time you can do that is when the first step is fast. So the shortcut here, when your first step is fast, just use the coefficients from the balanced chemical equation as the exponents. So that's how we could find the rate law when the first step is fast. Again, you can click through this if you want. If you want to talk about it on the office hours, we can. But because of time, we're not going to go into too much detail. Catalysts. So we should know a catalyst will speed up a rate of reaction. How do they do that? They lower the activation energy. And so we've talked before, right? If we have our normal uncatalyzed reaction in red, if we add a catalyst, the big thing to make note of is the hump goes down. So notice the blue, the hump. Don't worry about, oh, it has 2 humps. The main thing is showing that the humps are lower. Catalysts change the mechanism by which the process occurs. So it changes the pathway. It changes those steps that we take to a lower energy pathway. Heterogeneous versus homogeneous, we're just looking at if you have a reaction that is all gases, a gas catalyst is going to work better than a solid catalyst. The main thing with catalysts I would tell you to know is they lower the activation energy, and they lower it by changing the mechanism. That's the main thing I would make note of. And then that concludes kinetics for us.